My talk is about incoherent clocking, a method I've been investigating over the last couple of years as a potential clock and timing solution for the NGVLA. And my co-author on this paper is Bill Shillue from NRAO. I'm going to talk about the concept, some advantages, risks, and disadvantages, some FPGA code simulation results, what are the antenna clock stability requirements, NGVLA implementation notion, central site issues, and current research status. So the basic concept here is that at each antenna, we have an independent LO that's clocking the A to D converter as well as the down converter, which isn't shown. And we transmit that data timed with that same LO over a digital fiber optic link. And at the other end, recover the clock from that, and using round trip measurements and phase corrections here, measure what that frequency is doing versus time, and digitally resample and correct the data prior going to the correlator. The potential advantages of this over photonic LO distribution and clock steering are all COTS devices and methods can integrate into the science data link. Longer fiber links, since there are potentially longer fiber links, since there is no clock steering. We're doing a measure and correct operation. And what it means is longer fiber means the requirements for a more stable antenna LO, but the absolute frequency doesn't matter. And use commercial aerial fiber installation and methods and transceiver modules. Potentially can tolerate link dropouts and antenna power failures without requiring astronomical source calibration. The current risks and uncertainties are, is the transmit receive path over the fiber sufficiently matched for round trip measurement over two phase compensation? Is there phase wander in the FPGA PLLs that is confused with the antenna LO behavior? And of course, are there any unknown unknowns? Potential disadvantage is that the digital path forms part of the timing chain of the antenna. So this must be, any slips or glitches in this must be detected to avoid undetected coherence loss. So here's the incoherent clocking concept in a bit more detail. The antenna LO, clocking the digitizer down converter without worrying about the actual frequencies for a moment. Digitized science data is merged with this telemetry data, sent over the fiber link, turned back, where there's a recovered clock, and the difference between the outgoing clock and the recovered clock is measured with the round trip phase detector, and those phase measurements are sent with the data. This shows that the timing link and the digitized science data are on the same link, but they could be separate. At the central end, recover the clock from the data, measure it very accurately with a frequency tracker, filter out all of the fiber-induced perturbations and phase noise we know are not in the antenna LO, and use that knowledge to resample the data to a common clock domain before going to the correlator. So in a bit more detail, here's the round trip phase detector. We take a clock and use a DDS to generate what I call a tracer tone, a complex tone, and then do a complex correlation between that and the return clock going through another tracer to determine a phase error and a phase offset that we're tracking with time and sending over the telemetry data. We also do a round trip delay to the central end so we get a good measure of what the delay is. So here's some RTL simulation results showing the blue is the frequency versus time behavior of the tracer that I put in the model. The red is the raw frequency tracker result that has a huge amount of link jitter, and zooming in by 100 times, we can see that it's impossible right now to discern from the raw red measurement what the blue, the match to the blue. But when we put it through a low-pass filter, we can see it's tracking nicely. And if we do further analysis on that frequency error, and then the integral of that is the phase error, we can see that in this case, we have about 2.4 degrees of uncertainty in our knowledge of the 116 gigahertz LO phase, and that 116 gigahertz is the highest observing frequency, highest LO for the NGVLA. So what are the antenna stability requirements? Well, in general, the antenna LO must have an Allen deviation that's less than this AD cutoff or critical, at tau greater than this, and with the FIR low-pass filter with a cutoff frequency here. And this is derived from the Allen deviation phase change equation, where this is the round trip delay. This is the round trip delay times a multiplier, because we can't trust round trip phase measurements on timescales faster than that. And then we multiply by this filter multiplier factor, because we don't get the frequency, the actual frequency, out to the resampler until out of the low pass filter, and that takes time in an FIR filter. For example, on a 100 kilometer link, this is a millisecond, times 10 is 10 milliseconds, and then times this is about 144 or 150 milliseconds. There is some literature that Bill found that indicates the minimum RTN is 4, but we're planning for at least 10. And that's what the lab demo is going to help to determine, is if that is a sufficient factor. So then you get an Allen deviation plot where ADC critical and tau critical are here. And as long as your total synthesized phase and frequency behavior is below this curve at the down converter and the digitizer, then we're meeting the requirement. On this timescale shorter than tau C, phase noise is of no significance. It's sufficient to meet local needs, and we can't reliably measure it and correct for it anyway. And greater than tau C, frequency is changing, but we're measuring it and correcting for it, and essentially correcting down to this point. So for NGVLA at 300 kilometers, etc., we get these numbers for ADC and tau C. And for the 7G digitizer 8 effective bits, the numbers are about the same. And local oscillator that might meet this requirement is this NEL OCXO. Here's the Allen deviation curve for it. It only goes down to up to a tau of 100 milliseconds. So I've extrapolated here, and this may not be valid, but if it is, then it seems that this OCXO would more than meet the requirement. All of previous analysis doesn't include loop gain phase noise considerations. As the frequency goes up and you want to have lower phase noise, you want to drop the loop gain. And so that means a more stable LO. Likely that's not an issue, dominant issue for NGVLA, but it may be if this were be applied to ALMA up to 1 terahertz, for example. So the antenna implementation notions, Bill Shillue put this together after we discussed somewhat. So the idea is to have a small FPGA, the antenna LO, the first stage synthesizers, in a timing module at the antenna apex, and duplex timing link fiber to the antenna pedestal, and then integrate with digitized science data in the antenna pedestal FPGA. In this case, the FPGA looks like a repeater. This may have implications for digitized science data protocol. We can't tolerate on this timing link rate matching transceivers or repeaters. We have to have retiming repeaters, OEO repeaters, or optical amplifiers. And the second method is to send the timing link on a separate duplex fiber or color from the digitized science data, in that case, digitized science data protocol and switching equipment, etc., that it goes through doesn't matter. So here's a block diagram that Bill put together. Here's the timing module with the OCXO, first stage synthesizers, and a small FPGA to do this round trip phase detection over this timing link, which then gets integrated with the digitized science data, in this case, in the notion 1. The central site does have some issues. The frequency trackers operate in real time, and they have a continuous time component where they're doing the phase sampling. So any differential phase wander of the reference clock to the tracer phase sampling point across the central system may be confused with antenna LO behavior. So we must ensure that we don't get that kind of wander. And there's 3 ways of ensuring this. One is length matched and thermally stable clock distribution cables. For a small system in a single rack or a couple of racks, that's probably okay, but for an NGVLA, it's going to be a much larger system. Second method is to essentially have a cluster of FPGAs on a single board or a couple of boards, each handling multiple timing links going to the phase sampling points, doing a round trip measurement while delivering a clock, and those round trip corrections due to this cable expanding and contracting are just offsets into the frequency tracker. Third method is to cluster the phase sampling and frequency tracker into, again, a few FPGAs on one or a couple of boards where you don't have the central LO distribution problem, and then take those frequency measurements and send to the resamplers as messages in the correlator. So the current research status on all of this is we're working on a laboratory demonstrator using a Xilinx eval kit. All this nice stuff built in. All the FPGA code is developed and undergoing full chip testing and RTL testing, and NRAO is helping to develop software, and hopefully we'll be testing with hardware sometime this fall. So here's a block diagram of this. Essentially, I generate a broadband digital signal in the reference clock domain, drives a DAC into the ADC through the whole process, fiber, frequency tracker, resampler back, and then correlate that with a full resampled signal and look at the amplitude, delay, and phase versus time of that to see if if everything is stable and working as expected. If the correlator delay is changing with time after all this compensation, then there's something that's drifting and something that's uncompensated and that has to be fixed. Here's some RTL simulation results with this at the end, showing plots of these various points. And I should say in this model, I'm not just using simple, pure digital clocks. I'm actually adding phase noise with matching the Allen deviation of the clock synthesizers we're using, as well as matching the phase noise and wander and jitter of the fiber within the 10G SerDes jitter tolerance mask. So we have also contracted a fiber installation company to install long-haul ADSS, all dielectric self-supporting aerial fiber cable in the old DRAO 22 megahertz array. This will allow for fiber length testing up to 360 kilometers. Well, it's a little bit less than 360, but over 300 in about 10 kilometer sections with and without repeaters. Will allow empirical testing and exploration of temporal aerial fiber effects to determine feasibility over long haul aerial fiber. And we're doing 50-meter spans using about 2 kilometers of actual aerial 288 core fiber. And I'll show you a diagram of that in a moment. We also have funding to outfit the DRAO synthesis telescope with new receivers, digitizers, Talon correlator, and to test this on the sky. And we will be linking one of those antennas through this, this aerial fiber in various sections to see how well it works on the sky over long haul fiber. So this is just showing the setup of this fiber installation. Essentially, we get 36 duplex fiber links up to 10 kilometers each, and only using 2 kilometers or so of aerial ADSS cable. It would be cost prohibitive to actually run 300 kilometers of actual cable over poles, and this makes it within a reasonable cost. So here's the existing DRAO 22 megahertz array poles. They've been sitting there for decades, currently unused, and nicely positioned to allow us to hang aerial fiber. These are actually on a 7-meter grid, so we would be, spanning 50-meter span would go across about 7 of these, I guess, and going back and forth over the array. Anyway, I think that's my talk. I'm actually a minute and a half ahead of time, but we will stop there.